Things, welcome. I see some familiar faces, but I don't know. I have your full names. My name is, you may know me, Hossein Sadekpour. I know some of you, but not, of course, all of you. I'm sure this week we'll get to know each other. And that's one of the purposes of this sort of schools, is that you are in direct contact with the faculty at all times. You cannot get away from them, and they cannot get away from you. So a few things about the way we run this. We want to run it in a very sort of an informal fashion. Okay, so ask questions, and if you feel that you want to ask a question in person, there is time. There is a gap between lectures, and you can approach them. Furthermore, we have, of course, breakfast, lunch, and dinner together. Encourage everyone to sort of mix and mingle, so that you don't necessarily always sit with the same group, your cohorts, and so on. This I highly encourage. Today, we'll have dinner down in the biosphere, okay? And that's where the posters will be. So you should bring your posters with you for the dinner. There's a place where you can hang them, and they will remain even throughout the school too. It's okay. A few other things is the afternoons, of course, as you know, are free, and they're free in a way that for you to sort of take advantage of the time to sort of either discuss with the lecturers the problems that you may have or ideas and with us and so on. Except, of course, for Wednesday afternoon, which we will go for a hike. There is a possibility, because there is rain forecast for Wednesday, but it's, at least for now, it's forecast for Wednesday morning. If it is supposed to end by early afternoon. At which time then you should be okay to go. Otherwise, we will have to switch between Wednesday and Thursday. Okay. The only other time on in the afternoons, which is really not free, is tomorrow afternoon at 1 o'clock. Then we're going to all watch the Champions League game between Real Madrid and Liverpool. So what? You don't have one. The biosphere is open to us for tours, but it is recommended that there is a biosphere app which you can download for your iPhone or your Google, your Android phones, and use it to sort of as a guided tour when you go in. It's probably best to go in groups, but you're also welcome to go by yourself at any time in the afternoons, which are free. So aside from that, any problems that you find, whether it's here or in your rooms, you should bring it to the attention of me or Kim, who I'm sure you have all met, and I think that's pretty much the way we were going to sort of run the school. But any questions that you have for me right now, I'm sure that we will have time to catch up. Okay, so if no questions are, and I'm assuming that everybody has internet access and all of those things are all working fine. Okay, so without further ado, then we should begin. And the first lecture is given by Professor Gerhard Rempe, and he will talk about the slow polyatomic molecules. So please go ahead. We're using OWL as a sort of a way to take questions and record talks. So this, you can ask questions and this will capture it.
Actually, it looks like an OWL.
Yeah, it looks like an OWL.
Okay, Hossein, thank you very, very much for this kind invitation to speak here. I actually don't want to do this that you might know. I have no idea what molecules are. I will be looking forward to the other talks to learn about molecules. To learn about molecules internally. That's so complicated. That's so complicated. Too complicated for me. I'm seeing the absolute book first in principle. But at some point, I think I decided a little bit of a molecular physicist, or at least transfer some of the ideas of physics into molecular. Also try to invent some new strategies, new techniques, new methods or so over the years. And years means already 20 years or so. So this research started something like 20 years ago, when I just decided, okay, let's try molecules. And I tried for the complicated molecules, like the polyatomic molecules. I think almost no one was thinking about making polyatomic molecules slow and cold and wet. So, cold experiments, collision experiments, dense, collision events. Nobody was thinking about it back when maybe people were thinking about it, but there were no experiments like this. And I was not quite sure whether I should really do it. But the point was, I got a permanent position, and therefore I decided, okay, let's open it. And it's actually a lot of fun. And I will try to guide you a little bit through the last 20 years. It's a pretty unique research, right? I would say. And it's always good, but we start at the same beginning. And that's also why I'm so grateful to what's in here, because for me it's really a special event for to do actually. So maybe in the end I can learn more from this. Let's see. So that was one remark. The other remark is, okay, Jose asked me to give a relaxed talk. So today will be kind of easy. I will speed up a little bit in my next lecture, and then maybe in my third lecture, I will speed up more, and then let's see how it works. So for this, I need your feedback. So if you think I'm too slow, tell me. If you think I'm too fast, tell me. In any case, ask questions. As was mentioning, I didn't ask questions. Of course, after you, not for me. Okay, so having said that, yeah, it's about polyatomic molecules like these ones or these ones. This is a methanol. This is NH3, typically ND3 is maybe easier to work with. This is formaldehyde, a kind of favorite molecules of ours. This is fluoromethane or freon. It's one of the gases that kills the ozone layer. So we don't want to use it too much. Anyway, so these are the kind of molecules that are very interesting. We are not so much interested in the internal degrees of freedom, although we use them. We are more interested in getting these molecules slow. Okay? My next lecture will be cooling. Then I will tell you how to reach collisionally dense regime of the current temperature. Okay. So yes, you need new concepts, and I wasn't quite sure whether we could actually develop them. But let me give you some highlights today, tomorrow, and on Thursday. So having said that, let me start. I can't start. Can't start. It worked before. No, it doesn't work anymore. I'm sorry. Okay. Oh, so as I told you, this is really different. Different moment from what you say. Because I'm coming up with a personal perspective. Personal means, as I said, from a physics point of view, from a photonics point of view. I give you a kind of personal perspective of the research of neutral polyatomic molecules that we deal with. So this is a little bit an outline of what I want to say. The first thing is, why should we be interested in molecules? Okay, so maybe you all have an answer for yourself. I did not have an answer 30 years ago. So I will tell you a little bit of what I find necessary here. There are many, many topics and many views you could have, which are kind of interesting. So let's start at 20 years ago, 2001 or so, and then I will tell you about how to make these molecules slower. We developed a couple of techniques in the last 10 and 20 years or so, starting in 2003 and 2014, how to make them slow meter per second or so. These molecules that I showed in the first slide, then developed a couple of techniques which makes these molecules cold, pretty general methods, how we cool them, and in the ultra cold regime actually. A few hundred microkelvin is something that we can achieve. And we started with this around 2009, 2012 with some different techniques. Oh yeah, so yes, true.
That's long and important to be essentially the same thing.
No, it's not the same.
When I have a slow, you like the don't move much over the average.
What I mean by slow is they're just moving slowly into that meter per second or something. Not hundreds of meters per second.
The temperature will have some.
Cooling means that we increase temperature. Slowing just means we bring something which is moving fast for 100 meters per second. Is that a warning for me that I moved away too much from the old? Or it was you?
It's a Google from my end. I was just checking the recording.
But thank you very much for asking this question. I mean, today we're only dealing with slow, which doesn't give increasing phase sensitivity. And tomorrow comes the cooling, which means increasing
The temperature is the average kinetic energy. That's fine.
I mean, cool. I mean, you can make it always molecular heat, which is moving the sound the same. I mean, think of a supersonic. Okay, I'm a little bit so they go ahead. Think about a supersonic motor. It makes 1 Kelvin or something of the order of 1 Kelvin molecules, but they're moving with the speed of the upper gas, of the seed gas. Typically, they're not slow. They might be cold. So why in the end we want to set slow? To answer that question, I'm already addressing some points which will come. So what means slow? It means slow in meter per second so that we can track them. We can confine them in the lab. They're not flying away with high speed. And so the interaction times for flow molecules that are tracked can be increased in seconds and maybe in minutes. I will show you data. Cold means that we get rid of finally, that we get rid of the thermal excitation in the people. We are basically dealing with, hopefully at some point, quantity. To make quantity is visible and quantum fluctuation visible, we have to get rid of the thermal fluctuations. We have to cool. And dense means in the end, well, we want to see interaction. But this is kind of.
Well, there are questions. So I sure want thermal fluctuations. If you destroy one of this kind of methods, the question should be the thermal fluctuations mentioned. We have to see what the effects we have to. I would say we are okay. I mean, of course, it depends on the energy. I mean, of course, there are quantum effects that this is what I mean. But typically, quantum effects appear at low temperatures because their mass for overwritten by some fluctuations. Thermal fluctuations are just too large, typically. Maybe not always. We have an example where we don't have to do it. I mean, high temperature superconductivity, of course, it would be a quantum effect. It's still a newer form of biology, right? Because room temperature is the effects of photosynthesis and stuff like that. So, yeah, it's still out the way, it is out. Okay, but these experiments or these things are debated. Yeah, I'm not sure if I fully understand what they do. But in a nutshell, I would say you want to get rid of the thermal fluctuations in order to see the quantum effects. And this is what I try to outline here. And then maybe in the last 5 minutes of my third lecture, or maybe last 10 minutes, if I have time enough, I will talk a little bit about coherences and qubits and these things, which in the end is part of this conference, not part of the idea. Okay, anyway. So the whole idea is, and this is maybe one of the purposes of my talk. I don't want to tell you about all these fancy things about molecules that you can read in books, for example. I really want to advise you. This was my strategy, trying to communicate it to you. Do not follow the beat track. Do something new, ask questions, explore unknown territory, avoid the beat track. It's fun. I think I would say we had a lot of fun in the last 20 years or so with this kind of things. Okay, so let me tell you.
Yeah. What is the meaning of thermal fracture that we can assume experimentally now?
The need, so
The meaning of thermal fracture.
what do you mean by thermal fraction?
So you pull them down.
Yeah, it's what happens.
That's good. Thank you. Yeah.
Are you talking about the gas? So you have a condensed fraction and the thermal fraction.
Yeah. Thank you.
I'm not talking about that. And this is what we're talking about polyatomics, at least not so far. Okay. So be brave with the vision. I will tell you a little bit about that, but then in the end, be realistic. All PhD students want to graduate at some point. It doesn't help to tell them make a BEC of formaldehyde. They don't know how to do it. And then in the end, be happy with the result. So I hope that we will be happy with what I present to you. Okay, so let's start basically with a long motivation. Why do we want to leave all in this? Why not atoms? Why not photons? Why molecules? Typically, molecules are kind of complex. Well, my first answer to this would be they're here. They all consist of molecules. The air consists of molecules, the walls consist of molecules, our plane consists of molecules. Almost nowhere you can see atoms. But helium, for example, it's almost everything is made of atoms, which are made of molecules, which of course consist of atoms. And you want to understand what they say how these molecules are going to behave. For example, how do hydrogen bonds stick if you want? No, I mean, this is the water molecule and the hydrogen bonds. We all know about the hydrogen bonds. We all know about the anomalies of water. Water is a very special molecule, a very special liquid, a very special solid. Most of it comes from this bonding, from this hydrogen bonding. And one of the ideas would be, can we take two water molecules and then control bonding? Or maybe 3 molecules or 4 molecules, like we do with atoms these days. Like with atoms, we can do fresh power association, spin up and stimulate non-magnetic value passage technique, and so on and so on. Kind of standard in atomic physics. Can we do something similar with molecules? Can we understand in detail how hydrogen bonds evolve and how they develop, how the molecules arrange? There is not much theory. Maybe there's a little bit of theory. Maybe the theory can advise me more, but there definitely no experiments. It's for sure. No experiments with infrared water molecules associated. Let's say 2 water molecules to water supermolecule. So in some sense, there's huge potential for discoveries and new technology. So that's one motivation. This relates to the water. It's not just 2 water molecules which can form a bond. It's many of them. There are now 3, 4, 5, 6 of these, and they can actually be in one configuration. It's on one side, one configuration, or they can be the other configuration, exhibiting, for example, something like that. So does this configuration instantaneously flip into this configuration in a double well, like an ammonia molecule can flip up and down? What does it happen? I would be interested to learn about that. And of course, it requires low temperatures.
Sorry, question. Yes, I agree with Bob, like, when you mean double well potential, like, how would I understand the particle access?
I mean, if you, I haven't gone through the details, but look at this one here. This one is oriented like this one. I mean, there's this hydrogen connecting to the oxygen, or it's arranged like this one. So there are two configurations.
Those are stable, which are stable compared to other,
That's very cool.
compared to other, assembly, structures.
Yeah, what do you mean by stable? They can flip from this side to that side. If this is a double bond potential, like outlined here, this configuration lives in this part, this configuration lives in the other part, and of course they can tunnel. The question is, what is tunneling time? It's what. I'm just mentioning a few examples to you, and probably every one of you can come up with more examples. So this may be a little bit technical thing, like polyatomic. I think polyatomic is pretty simple. They're simpler than many other molecules, at least technologically speaking, and I'm an experimentalist, so I need to implement some technology to that. I think they're simple. Why are they simple? Well, they exist naturally. They come out of the bottle. I don't have to synthesize it. Don't have to laser cool atoms and then associate, for example, the atoms into molecules. They're simple. They come out of the bottle. They exist naturally in space on Earth, which makes it interesting. In interstellar space, you can see this molecule. Second, they're chemically stable. Okay. They're not necessarily, okay, they are radicals, but the molecules I talk about are chemically stable, closed pairs, which means they don't have a spin, not an electron spin, so they hardly have a magnetic moment. They have a magnetic moment from the nuclei, but not from the electron shell typically, which makes it easy to deal with because they're not magnetic. Atoms are magnetic, and one has to really work hard to control all the magnetic fields. Here is much simpler in some sense. So they're easy to handle, easy to control. As I said, they come out of the bottle, they open the valve, the molecules come out and do its job. No laser, no nothing. Simple, pretty simple. We don't need chemistry, we don't need to understand chemistry. They're just there, the molecules are just there. Only physics. Which I, as a physicist, like, okay, maybe some of you are in chemists, but I would say it's kind of simple. Even that you understand physics. They can be controlled with electric fields. I mean, most of the polyatomic, not all, I will mention, I will come to that, have a permanent dipole moment. So this dipole moment talks to an electric field. So with electric fields made by voltages or a few kilovolt or so, which is kind of very convenient in the lab, you can control these molecules. And then in the end, which I will explain to you tomorrow, we hardly need a laser. For cooling the molecules, we need one laser for cooling, just one. So mentally, very, very simple, just one laser. We need microwaves, we need radio frequencies, but we just buy the microwave, buy the radio frequencies, easy to use. So
You said
in some sense, it's very simple.
you just think they all have permanent backbones. Almost.
I will give you two examples. So here, they are polarized. This is my molecules, one of our favorite molecules that I mentioned before, CH3F. Fluoromethane, for example. It looks like this. There's a stable rotation, and this is something I want to point out. There's a stable rotation around an axis, which is outlined here, which is along the dipole. Okay, so taking the angular momentum stabilized orientation of the molecules in free space, in an electric field, for example, and it will rotate like this. A very, very simple picture. Okay, this is why it shows more or less linear structure. Okay, there are some delicate issues I mentioned, but more or less this is a permanent electric dipole moment stabilized by the rotation of the molecule. Very simple classical. Maybe too simple to explain all the features of the experiment, but this is the basic idea. And this is, for example, something you don't have as a dimer. A dimer molecule, video sealing or whatever, you associate rubidium with cesium, or cold rubidium and cold cesium, you associate rubidium cesium, there's no stable rotation along the axis. Right? That's why these molecules typically do not show the linear star shapes. The situation is somewhat different, and I will explain to you in terms of the experiments. The situation is completely different from water molecules. Water molecules have an entirely chromatic star shapes because in the lab frame they have no dipole. I will explain to you why. In terms of classical physics, I don't need all physics here. In terms of classical physics. But what it means in the end that a water molecule, the electric dipole moment in the lab frame is exactly zero. In the lab frame, not in the molecule. In the lab frame. I will explain to you more given this the simple pictures. But think of the water molecules as taking in all different directions. More reasons why polyatomic are interesting. They can be chiral, so we can do chirality experiments. And for this, you need at least four atoms. Four atoms, a molecule consisting of at least four atoms. So a chiral molecule is outlined like this. So this is a molecule, and in a mirror image, it goes like this. But we need at least four atoms to do the whatever experiments these are. There are other reasons why polyatomic molecules might be interesting. For example, there could be a chemical resource for cold atoms. Think of a cold or ultra cold water molecule. Maybe it's hard to make that, but let's assume we have that. So it's ultra cold water molecule. We can dissociate them, at least principle, into an OH and an A. So we would have very cold H atoms, or very cold OH molecules. The principle is followed. Okay.
But in association, there will be a lot of.
That's a sanity. That's a sanity. I mean, I think we talk about here. The simulation normally implemented passage techniques will bring cold molecules, so cold atoms into cold molecules and back. And the atoms that are made from associating the cold molecules will be slow. Not necessarily have enough temperatures. Depends on how you dissociate them. So in principle, these cold molecules could be a chemical resource for atoms which cannot be laser cooled. Hydrogen, carbon, nitrogen, oxygen, fluor. Maybe at some point that's interesting. Okay. Just an idea. Well, why do we want to have them cold? Well, first of all, they exist. Cold molecules do exist. They exist in interstellar space. For example, there's a picture of the Bohn nebula. It's a rapidly expanding gas in interstellar space, and it has temperatures below Kelvin. Molecules do exist. So we want to have them in the lab, and study, so to say, their features in the lab, and then maybe learn about interstellar physics. Why cold? Well, they can be quantum or used at least for quantum experiments. Quantum technology is, of course, one of the topics of the school here. And these hybrid systems, maybe solid state devices, this is superconducting chip architecture, superconducting qubit chips architecture. We can maybe combine them with molecules. Molecules as a memory for qubits, quantum memory for qubits. Molecules have long rotational states. I'll talk a little bit about that. And they can, for example, store qubits. Qubits coming from the superconducting architecture. Qubits do not have long memory times. That talk to phonons, that talk to solid state environment. Very different. But molecules might be much better. So combining the two technologies, cold molecules in the vicinity of, let's say, some superconducting architecture, would combine the best of two worlds. Two worlds being superconducting qubits and molecules. Interaction between the molecules, chemistry, cold chemistry is interesting. They can interact. So let's think about this one. I think, John, this is one of you. Is one of you? I think I took it from one of you. So this is, for example, a formaldehyde molecule and an OH molecule. Coming in slowly, and then interacting with each other here, they're colliding with each other, and what comes out is maybe a water molecule and a formaldehyde which is missing one hydrogen. I don't know how it's called. And there are many interesting chemical reactions that can be started at cold temperatures. At cold temperatures, you would kind of think that chemistry is falling out. But this is only valid if you have to overcome a potential barrier between providing partners. At low temperatures, you have the possibility to, for example, to tunnel through the barrier. Tunnel through the barrier, and you can make a nice chemical reaction. And this is typically not available at room temperature because phase density is just too small. The energy spectrum over which we are at room temperature, the molecules are distributed, it's just too wide to see a very narrow, let's say, vector resonance or shape resonance or something. So we need to make the molecules cold, increase phase density to see this particular condition.
Now, what do you mean by Miss Cold and travel through the barrier?
You want to have sufficiently many molecules exactly at this level. Okay, same thing about the potential landscape. So this is radial coordinates and this is energy. So when molecules are far apart, they typically have to overcome a barrier, centrifugal barrier or some barrier in order to make a chemical reaction in the electrons. Very generally picture. But they can tunnel through. For example, there could be a stage here. So you need to put in molecules and this particular energy. They can tunnel through and make a condition. I think we talk about these things. Maybe I don't know. So, but in order to do this, you need to sample, you prepare that this particular energy.
Basically, you're saying
And typically, a reading temperature that is distributed all energies. So only a very small reaction will go this. Too small to be observed. If you can really cool, then makes the energy spread. I think that partly answers your question. Make the energy spread of the molecule is very small. Basically comparable to the width of the level. It's only this political context.
so you're referring to with a resonance, the opposite or something like that. Like Miss Cold, but in other aspect, Miss Cold is hard for you to actually tunnel or just go over there.
Yeah, you don't. Yeah, I think you don't want to go over the barrier because it would be better hands. I mean, if this barrier is smaller than each of the shock KD, they also have each of the shock. If the barrier is smaller, they can go over it and do something. If they are very cold, they cannot go over because they are too cold. But if you give them a certain energy, which matches this energy here, and they can try to. And go there. Just an example, very simple, but still at the motivation stage. and you can think about many different things, but this is what I basically have in mind. This whole chemistry here. They do interact, they have a dipole moment, as I said. Or in case they have a dipole moment, they interact. For example, there are these two molecules, one molecule here, one molecule there. This has a dipole moment, this has a dipole moment, so you can think about electric field lines like this. And then you can kind of think about how long range is the interaction between the two molecules. And in order to do this, you could put the centrifugal energy equal to the dipole energy as this. The centrifugal energy for 1 unit of angular momentum would be relative in the quantum of 1 unit of angular momentum.
And if you do this, you arrive at an equation which is basically like this one. The distance is proportional in SI units, proportional to the dipole moment squared and the mass of H bar squared. Typically, it's 1 micrometer. Dipole moment is something like a 1 micrometer. Wow. 2 molecules separated by 1 micrometer. Here, what? Think about 1 micrometer. 1 micrometer is typically all this. I mean, typically molecules interact at distances which are more or less normalized interaction lengths or some chemistry interaction length, which is much shorter. And this is the universal interaction because we don't have to care about the internal structure of the molecule. It's pretty universal in the simple terms. Still motivation. They interact. The energy at this interaction distance, in order to see this, it's experimentally hard. In order to see this, you have to go to temperatures or energies, which are basically the dipole moments, the dipole interaction, the dipole moment divided by the distance cubed. The distance was a micrometer or so, and the dipole moment is maybe a 5. So you have to go to temperatures way below 5 Kelvin. So this is hard to achieve with polyatomic molecules. Everything I'm saying here is polyatomic molecules. And these wonderful experiments with photo-associated or Feshbach-associated molecules from atoms. They can reach this regime. And for polyatomic molecules, it's really. Okay, you can do precision experiments. I mean, principle, you can slow them down with the idea, have them slow, have them interacting with some fields, do some Rempe spectroscopy over some distance. I mean, this is a picture I took from one of the highest publications. I think I should replace it by maybe one of the beautiful pictures and beautiful experiments from the Harvard collaboration. One measured with the electron dipole moments. But I took this from behind, so okay. So yes, you can do precision experiment, Rempe experiments, once you are able to make so EDM measurements, time reversal solutions, things like this. So that's fundamental physics. Why slow? I already addressed it to you. We want to track that. They should have little kinetic energy in the lab pack. Let's travel. The most simple configuration to travel a molecule is a quadrupole, electric quadrupole. Okay, think about electric quadrupole like this one. Positively charged electrodes here and negatively charged electrodes there. And it has an electric field minimum in the center, and the electric field increases when you go away from the center. And so some of the energy levels of the molecule, due to the Stark effect, go up in energy, and some of the molecules go down. So in such a configuration, it's easy to trap low-field seeking molecules. You can't trap high-field seeking molecules that would be attracted to the electrodes, but you can use the low-field seeking. Yeah. And the trap depths for this simple configuration here is very, very deep, and that's the good news. For this two-dimensional configuration I'm showing here, the dipole energy, dipole moment times the electric field, basically is of the order of many, many kelvins, maybe up to 10 Kelvin. Of course, it depends on the electric field. But let's say in the lab, you can easily apply 100,000 volt per centimeter. I mean, look at the scale here. This is a few millimeter or so. So you have to charge the electrodes by up to maybe 10 kilovolts, which is not difficult. And you reach the electric field of the order of 100,000 volt per centimeter, and you can track that and can, wow. Can you imagine how you can get this with atoms? Atoms have no dipole moment. Don't have this interaction. So atoms is completely different. So in some sense, it is a very easy tool that we exploit a lot for tracking molecules in 2D like this one and also 3D. We'll explain to you how we do this. Okay, so that's the end of my basically long motivation.
Any questions? Any further questions? So now the idea is basically, yeah, we want cold elements, we want cold molecules, we want slow molecules, and we want dense molecules. Dense for the interaction, slow one for the trapping, and cold to get rid of the thermal phase. And then maybe in the end reach a regime where the molecules collide. So I will talk about this today, this tomorrow, and this in my third lecture on Thursday, more or less. And we will reach a regime which can be associated with this kind of accident. The big question is, how do we do this? Polyatomic molecules, how do we make them cold? How do we make them slow? How do we make them dense? And what happens? I would say, in principle, it's all pretty open questions. At least when we started this research many years ago, deeply unfounded. Okay, so let me begin. First of all, we don't need to make slow molecules. There are plenty of them available. Just take a gas like this one. Here's room temperature, 300 Kelvin, let's say, 10 to 5, 100 hectopascal. That is 1 bar. You have densities of something like the order of 10 to 19 per cubic centimeter. As a fraction of slow molecules, let's say 20 or so meter per second, it's velocity here. You have 10 to 15 cold molecules per cubic. This is the density of a Bose-Einstein particle. Given taken all of that. So why wasn't it? They're there. They're just there. The question is, once we have identified the slow one, let's say this one, collide with the fast one, because the majority is fast. No? I mean, there are 4 orders of magnitude more fast ones than slow ones. So in the next fraction of a nanosecond or so, it collides with the fast molecule and it's no longer slow. So the environment is just not the environment we would like to have. So we have to do something with this. So we have to separate, let's say, the fast ones with the slow one from the slow one. And this relates a little bit to Maxwell Demon, 1871, and so, who devised development experiments of separating the gas of molecules into a gas with the hot ones and into a gas with the slow ones. So these are the slowly moving molecules instead of fast moving atoms. Basically, he picks out or he picks the fast ones into this direction, the slow ones into this direction. So there's a long story behind Maxwell Demon. I don't want to go into the details. It's just a question of how can we realize, how can we make such a, how can we separate the slow and the fast molecules? Well, there was a first experiment actually, and I don't know how many of you know this, with Zacharias at MIT, 1954. Do you know this experiment? Have you heard about this experiment? Yeah, skip this slide. Good view. So there was an experiment in 1955, 70 or so years ago, on making slow molecules in a fountain. Everything that is known about that experiment is written on this page. Invited papers on molecular beam experiments. There's a title, Precision Measurements of Molecular Beams, and there's an author, and there's an affiliation. There's no abstract. There's no text. There's a little bit, there are a few sentences in a normal Rempe book, for example, molecular beams. But it's not very illuminating. So this is everything that exists. So it's hard for me to talk about it. No.
Was never published, or this was never published. This is a publication. And it was maybe something for a publisher.
I think from the internet we can find it in. I also want to write down that so if we can find
It's very easy on the, so maybe it's some talk, but he was giving some.
Yeah, there was probably a talk, but this was before Zoom was invented. As far as I know. Anyone of you know that? You must have invented before it was physical. Yeah, this is in this is, I think it's taken from physical dynamics.
Really, Zacharias would want to publish the details of the experiment. That happens.
There's nothing.
Really?
Well, we have 3 afternoons, we can search. I haven't found anything. But I know a little bit of how it was working, because there are pictures on this. I actually talked to Ray Weiss. Ray Weiss was a very young student at the time, and he worked with satellites of this experiment in the 1950s, 1954. And there are a few pictures. No? So you can see this experiment actually exists in this picture here. And I was told that this drawing here, you see that the drawing that's the wall, this is the only thing that exists on paper from this model, from this experiment. This is what I was told by Ray Weiss. So apparently, this experiment was not successful. And this is what you can read in normal language. There's no paper, there's only this little chapter, little paragraph, one paragraph, a few lines or so, in normal language book. And the problem of this experiment is the following. So let's assume we have a molecules in a container here and a little opening. And let's say 300 Kelvin, and there's a vacuum all over the place. And Zacharias wanted to make this home. So the fast molecule food out with hundreds of meters per second, but as I said to you, there are slow molecules, 10 meters per second, or maybe only 2 meters per second, and they go up only a little bit and then come back down. So the idea is to do an experiment with molecules which are just coming up and falling back down, and obviously these molecules are moving at the speed of 2 meters per second, so not very fast. And this is what they wanted, because they wanted to do precision experiments, vantage spectroscopy. These molecules are moving through the interaction zone twice, once on their way up and once on their way down. Now the issue is that they are fast molecules. And the fast molecules kick out the slow molecules. And because the slow molecules are very small, even the large impact parameter of the fast molecule changes the direction, the momentum, the direction of the slow-moving particle by a loss. The energy is not changed much, but the momentum is changed. So the slow molecules hit highly fast ones, not head on to them. There's a large impact on. They get this large momentum transfer that is kicked out, they go to the side. And so the spread of angles over which these molecules scatter is extremely large. You will not see a molecule coming back down to the same place. It just dilutes. This is my interpretation. Okay, it's my interpretation. The formula is very wise, and I confirmed it, but this is my interpretation in the end. So the idea is, the whole idea is, if the energy transfer is small, momentum transfer is large, just keep them in a guide, traps them, makes this colorful guide, for example, some guide here, which brings the molecules which are kicked sideways, which brings them back and guides them to a place where we want to have them. Basically. That's its one view. And not getting, because the impact parameter is so large, and not getting fast, it stays low, but the angle is large. And if you present the molecule with this large angle, typically somewhere, to guide them. So that was basically the thing that we started about 20 years ago. We wasn't quite sure whether that would work. You know, but as tried it, and at some point I showed you, I talked to Ray Weiss about it, and I couldn't resist to show you this so to say, this response. I think that the idea of collecting a scattered slow atoms and its realization that the kinetic energy has changed little it's much smarter than anything general surmise or I was thinking, oh, it's he got a Nobel Prize. Anyway, so in 2003 we made this experiment, and there's one more thing to it. There's one more thing to it which I think is important. I showed you this velocity distribution with a small fraction 10 minus 4, so of the molecule being slow. This is a little bit different view in the sense that now we plot just the, let's say, what I call one-dimensional velocity. There's a reservoir of molecules, like the room, and there's a door. You open the door and the molecules can come out. These are the molecules we want, because they go in this direction. There are also molecules going this direction, against the wall here. We don't want them. So it's interesting to plot as a function of the velocity in the preferred direction, plot the velocity distribution. And of course, there are equally many molecules going in negative direction than molecules going in the positive direction. But there's a maximum at zero velocity. So most of the molecules go sideways, not going to the door, but they go sideways. And they're not, this is not considered here because we just plot the velocity along one certain direction. And there's a maximum here. So basically what we would like to do is just take these slow molecules. Let's assume this is 10 meters per second or so. Just take these slow molecules in a reservoir and take them out. And it's maximum. Maximum. So there are really plenty of slow molecules available. I think this is the main message that I'm trying to communicate.
This a little bit contradictory to the other figure you showed us. So what is like for 10 to the 9 is small part in
the total number and the magnitude of the velocity. But in the end, I'm not interested so much about the magnitude of the velocity. I'm going to work with some molecules which are slow and they're going this way because I'm there. This is the reservoir here, and I want to send it to you. I'm only interested in the molecule going to you. I want to give you slow molecules because you want them. Yes, you want. You want them. So this is the velocity direction. Okay, so basically the idea is not to take a reservoir of molecules and make a hole in it and let the molecules come out and shoot them into some guide, but bring the guide into the reservoir and take out all the slow molecules which are moving in one direction. You get the point? So this is basically how it works. So there's a reservoir here which we can heat or cool some temperature between 5 Kelvin and 300 Kelvin. Then there's a colorful guide which we really stick into the reservoir as far as possible. And then immediately make a bend and separate the slow one from the fast. Okay, and this is maybe only a few millimeters also. So the more, and maybe even less. So it's bended here, the slow ones come out here, the fast ones come out here, and in fact we can recycle the fast ones to bring them into the reservoir. So in some studies, maximum beam to some extent. So that's how it looks like in the picture. So this is the guide, colorful guides. These are the 4 electrodes. Each of them charged with something like 10,000 volts or up to 10,000 volts. And you can bend them like here. So the molecules are guided by this guide, and then there's a sharp bend, radius of curvature, so a few millimeters. And they make it around the bend and go into the direction. So the idea is never let them go the flow molecules move. But don't let them untended. Like the way of the kids on the plane. And we have the molecules, the slow ones. Don't leave them unattended. Always keep them. And in this way we hope to get as high density as possible.
Why do the top ones don't go to the path?
Excuse
Why do the top ones don't go to the path? Or they do?
the hot ones go straight, they don't make it around the bend. They don't make it because of potential Google force. It's something which I call the hybrid exit phenomenon. If you drive on a highway with how many miles below 5 miles per hour, and then the sharp bend slow and leave the highway, you have to slow down. You can move. If you get too fast, you have to keep going. And the fast one just keep going. I'm too slow, I'm way too slow. I prepare too many slides. Well, that is how much time do I have? And it's something like that. Yes, so many less time. I'm waiting. These people do that, that's too slow. Because there's so many slides coming. But okay, I get you can go through the mathematics, but it doesn't have the full force which half ones. It's not a full barriers.
Worry about the surface absorption, for instance.
Excuse me?
Surface absorption, surface collision of the molecules, or that as you got in the line.
But we have collision to the guys.
But the surface is okay.
No. Here, I mean, this is 10 Kelvin. No? Of course, the molecules which have a higher temperature, higher velocity, goes higher than 10 Kelvin, which is kind of strange thing because Kelvin has nothing. 10 Kelvin is temperature and velocity is energy. But you understand what I mean? No? It's a kinetic energy which corresponds to K Boltzmann minus T and temperature at 10 Kelvin. Of course, the higher the fast ones can hit the electrodes, yes. But the slow ones not, because they just repels and low field seekers. They just stay in the center. Okay. So now comes our water experiment that I promised you. Here's a water molecule, OH2. H2O. These are the two hydrogen, this is O. It has a dipole moment along this axis. The oxygen is charged negatively and the hydrogen is charged. It's somehow more positively. So the dipole moment goes this way. And then of course the molecule can rotate. And the principal axes are denoted by A, B, and C. And the rotational constant along these axes, A, B, and C, is in units of wave numbers, is 27 wave numbers, 14, and 9 wave numbers or so. Now the dipole moment has only a component along the B-axis. The dipole moment is about 2 dpi. But it's only along the B-axis. Okay. But now look, the B-axis has a moment of inertia, which is in between the large one and the small. As you all learn in physics 1, first semester, second week, second month, rigid body is the rotation of a rigid body is unstable on the axis which has an intermediate moment of inertia. This is what you learn. You probably forgotten it because it's so long ago. But now you have before. So it cannot rotate stably around the axis B. It could rotate around stably around axis A and C, but not B. But around axis A and B, there's zero dipole moment. And that's why the dipole moments, from a classical point of view, dipole moment of a molecule aligned along the B-axis is not stable in space. And that's my picture of why water molecules do not have a problem with dipole moment there. It rotates away, rotates to zero. After a few rotational periods, which is very fast, dipole moment has average effect. And there's a lab plane that no dipole anymore. So this is for water. In the lab plane, dipole average is to zero. You can replace the hydrogen by a T, but nothing fundamental changes. The rotational constant changes a little bit because the T is a little bit heavier than H, well, twice as heavy as the H. But nothing fancy happens otherwise. For example, if you calculate the energy level diagram of the water dipole, the water molecule, the lowest lying energy levels, as a function of the electric fields, they're all correct. They're all quadratic. Which in the end means you have to reduce the dipole moment. They don't have a permanent dipole moment left. You reduce the dipole moment. And I think this can be explained by my classical picture. Now let's do an experiment and replace only one of the H molecules with a D. Make it asymmetric. So this is DHO. This doesn't change the dipole moment. Dipole moment is more or less the same. Because the dipole moment is not sensitive, not so sensitive to the mass, but it changes the rotational axis. Because now the D here is twice as heavy as the H. So the rotational axis A, B, and C are now rotated in space. But the dipole moment changes. And that means that the component of the dipole moment belongs to the A-axis. And the A-axis, as I said, is a stable axis, stable rotational axis. And the dipole moment is non-vanishing, which in the end means that HDO should show a linear structure and should be much more easy to use in an experiment. And so we did the experiments. So we looked at how many molecules can guide. Flux of molecules in this scenario that I outlined before, the colorful guide. So the source and the colorful guide at the end, that the colorful mass spectrometer, which measures how many molecules we have. So this is the colorful mass spectrometer signal as a function of the electrode voltage. And you can see that the HDO molecule with its permanent dipole moment has much higher flux than the D2O and the H2 molecule, which has a reduced dipole moment. It's much smaller flux. And this shows, so to say, for this point, that the trapping potential is 2D guiding, and the trapping potential in 2 dimensions. It's much larger for the permanent dipole moment H2O than for the induced dipole moment D2O and H2O. You can also see that the slope is different. And this comes from the fact that here the flux is proportional to the electrode voltage or the electric field with force power, and here's only the second power. If you use the dipole moment, the dipole moment becomes larger and larger. It's a large structure, and that favors large electric fields. So that's why the slope here is so much different. So I think with a simple configuration, no laser, nothing, very simple configuration, you can always take a moment. You can learn a little bit more about the molecules. For example, this is the shape, this is industry here. Where we have, so to say, a nozzle here. We inject the molecules into this guides and we bring it into another chamber, so differential pumping regions like this one and like this one. And for time of flight, this can be a long distance. Actually, we have this distance up to something like a meter or so. We can just determine from time of flight the flux of molecules which is arriving, time resolved, and from this we can deduce the velocity distribution. And this is how the velocity distribution looks like. It's peaked around 60 meters per second. It falls off for higher velocities, so we don't see anything above 120 meters per second or so, and this is determined by the rate of curvature of this band. And then apparently the molecule, the flux of molecule disappears here. But I will explain to you or argue that this is not that comes in a second. But before I do this, we can also have many pieces of this guide, all separated in space, but also separated by being able to apply different voltages to the different pieces here. And we can switch on and off the guide in these pieces in synchrony with a certain velocity class. And in this way, we can guide molecules which have a certain velocity, maybe not the other ones which do not have the velocity. And this way, we can get a very sharp velocity distribution of, let's say, around this one here, 20 meters per second plus maybe 1 or 2 meters per second. Very sharply defined. So let me explain to you where this comes from. So a quadrupole mass spectrometer measures density, and this is what we see here. But in small velocities, one can show, and I show it in the next slide, and I don't want to go with it because I'm losing my time. We measure flux. So it's a little bit an artifact because the way of how we measure this, our mass spectrometer, is that for high velocities we measure density, and for low velocities we measure flux. Of course, flux is proportional to velocity, and that's why it goes up here more or less linearly. There is a reason behind this, and I could show you there's some mathematics involved, but maybe you just believe me that this is an artifact and this is how it is. So let me explain to you. This was two-dimensional guidance. So let's go to three-dimensional. So let's try to step some more. So the first step we built was one which is immediately compatible with our colorful electric guide. So this is guide here with the 4 electrodes. Remember, it's bent and it's bent a couple of times. It goes to different pumping regions. And this nicely connects to a colorful trap, which is arranged like this. So this guide and this guide, for example, is connected to this big electrode. It has an exit here, which is also again connected to a colorful guide. And then the next one here, this one and this one, is also connected to a ring. So this is positively charged, this is negatively charged, meaning that this here is positively charged, this is negative, positive, negative. So we can build a multiple trap, easily fillable, continuously fillable with molecules from this trap. The trap didn't work very well, I should say. The work didn't work very well. We had lifetimes of only 100 milliseconds. So it's too short to do a real experiment with. But we had temperatures on the order of 300 millikelvin. Temperature meaning the velocity distribution corresponds to some temperature. So we designed a better trap. Now comes a little bit longer explanation of how we type molecules and benefits of this trap is. So we built a completely new trap. It's based a little bit on the design that I showed you before, but it's now more complex and it has a more multiple character. And multi means something like 20, 30, 40 or so folds, or maybe even more. Okay, let me introduce you this trap step by step. It consists of 2 parts. One part is like a plate capacitor here, and the other part is like a plate capacitor there. Why do we need the 2 plates? Well, we want to bring molecules from here to there, or from there to here, and or confine them only here, and one lets them go there. So we have basically 2 regions where we can do experiments with molecules. That's the idea. I will tell you what kind of experiment. But we can apply a homogeneous, more or less homogeneous electric field. Let's say 1 kilovolt voltage here and 1 kilovolt voltage there. The distance between the plates is a few millimeters, and the whole thing is intelligible now. So this gives us homogeneous fields to address the molecules, laser, microwave, radio frequencies, because they have a well-defined star shape. But this is not a trap, of course. This is just a capacitor configuration. So how do we make it a trap? Well, we structure this with micro electrodes separated by something like a few hundred micrometers or so, positively, negatively, positively charged. And that creates a configuration like this one, which is repelling for a low field seeking molecule. That I try to explain with the carbon. So this is just multiple mineralization of our carbon spectrum. So the electric field is increasing for a molecule approaching the surface and decreasing for a molecule increasing with distance from the surface. So in that sense, this plate, which is this one, all the way down and also the lower one, serves as a repelling part of our electric trap. And then, of course, the molecules can escape to the side. They cannot approach the plates, but they can escape to the side. And that's why we have a highly charged, high voltage electrode around the whole thing, around the periphery, basically, which repels the molecules from escaping.
That's a little bit the scheme. However, the superposition of this electric field with a homogeneous field creates holes. Here is a little bit of blown up region. So this is the microstructure here, plus minus, and so on. With electric field lines as shown here, and then there's this homogeneous fields. And let's assume the positively charged electrode is below, and this is the negatively charged electrode. Then this electric field interferes with this electric field and it creates zeros. Plenty of regions where the electric field is zero. The molecule moving to a zero electric field might enter as a low field seeker and come out as a high field seeker. So we don't want that. So we want to fill the holes. So how do we fill the holes? Well, our electrodes are these stripes here, and the stripes have a structure which is wider here and narrower there. For the positively charged. For the negatively charged, it's just the opposite. So it's wider here and narrower there. And that creates an electric field along the structure. And this electric field along the structure plugs the holes in the column configuration. So if I go back to this, it's the electric field that goes into the board, into the white board here, or into the spring. Electric field goes in or comes out, depending on the direction. But when a molecule flies through a region of zero electric fields, it's not zero anymore. It sees an electric field which slowly changes the direction. And the molecule, if it's slow enough, can follow that direction and it can. So the orientation along the field is preserved, which is nice. But then it has another issue. Of course, they are minimized the electric field along this line. So molecules can in principle be guided along the line. Then they escape the line. And we prevent the escape from making a U-turn or pitching a U-turn on the place. Molecules can go along, move and come back, come back, oscillate back and forth. So it's a pretty fancy configuration. So the escape traces are more or less closed. This is how it looks like. It's I don't know if you can see it. Basically, it has all these stripes here, all these stripes which makes a depending electric field for the molecules. But you can if you really look carefully, you might even be able to see that there are chambers, because it's a little bit larger here than it's there. 0 minutes, no?
Well, if you have pure electric, you can cycle some of these through and continue with the.
This is I'm just a few minutes, sure. So this is how it looks like. Basically, we have this multiple structure here. We have the molecule guides, which brings the molecule in on this side, colorful guide on the other side. It's the output guide. We can have the molecules coming out. Yeah, and this turned out to be a very nice track. So this is a picture here. So the cable, the input guide for the molecule is the output guide for the molecule, and this is basically the configuration in the vacuum chamber. So now let's fill this trap with molecules. The nice thing is it has a box-like potential. There's this independent electric field very close to the surface. And otherwise, it's a flat bottom. Yeah.
What's the main reason that you pressure are very fast?
130 milliseconds.
Yeah.
It's more the bench fire. I can do better. Yeah, coming. Next slide. So we have steam balls for good confinement, something like many kelvins. We have a flat bottom in the trap for doing spectroscopy, addressing the molecules with lasers, with radio frequency, with microwaves. So it looks like a box like this one. Then we have an externally controllable offset electric field, so we can really tune our molecules to certain electric fields that we want to have. And this is where we trap. So this is we fill the trap, and we let the molecules. We switch off the filling by switching off the guiding.
switch on the filling, and we just see how molecules escape and how long are they stored. And we show the track lifetime here. Molecules taken as a function of life, as a function of old time. And you can see it takes 10, 20, 30 or so seconds for the molecules to escape. So this is a much better fact than the other one. I don't want to go into detail. This is much better, but we can talk after that. What you can also see is that if we make it a shallow trap, and just applying low voltage electric fields, you can trap only small molecules and they have a longer lifetime. And if we make it a deep trap, which means a high electric field, it looks like we are trapping fast molecules which have a shorter life. And this comes from the fact that fast molecules can not make it. I mean, you remember there's minima which we find field, but if the molecules are too fast, they can't organically follow. So basically, they cross all these wiggly potential, a little bit wiggly potential, close to the surface at least, and they can make a flip. And that's why slow molecules have a much longer lifetime. So here's, for example, one of our records samples after cooling, and I'll tell you about cooling later. But once we cool them to, let's say, millikelvin temperature or so, we can observe molecules staying in the trap for about a minute, which is pretty long. Really gives you plenty of time to do experiments. So this is a typical trapping time. Or fluorescent. I have another couple of slides for spectroscopy, but maybe I don't have to show them to the audience, depending on how the chairman.
You can shift to your second lecture.
Okay, shift to my second lecture. Speed up a little bit in my second lecture for that point in the full of slides. Yeah, okay. So anyway, we do spectroscopy, a magic spectroscopy. I just showed you the results. We drive transitions here for molecules which are 2.6 millikelvin, and I tell you how we cool them. 2.6 millikelvin. You see narrow line with spectroscopy, something like a few kilohertz lines, and a typical transition frequency of 360 gigahertz. What gives us a resolution of 10⁻⁸, which for molecular physics is quite something. For atomic clocks, this would be nothing. The atomic clocks are 10⁻⁹ or so. But for molecular physics, is something. And this is what trap molecules trapped in this trap that I tried to outline from actually. Okay, so this is my summary. I presented an efficient method to skim, guide, and trap with electrostatic fields, slow polyatomic molecules, which have a permanent electric dipole moment to room temperature. Just take the molecule out of body. That's a summary of my long talk. Thank you very much.
I don't know about you, but I wish I were exposed to so many technologies when I was in the graduate school, but yes. So I would suggest, in the interest of time, that while John sets up, that you come and ask your questions you have from Gerhard, but of course then we have lunch and we have dinner, and then you have cake, yes. But yeah. The technology involved, both John and I are theorists. So.
Any questions on the way? Which was good. Which was good. No, which was good. Oh, yeah. So Dave is online and coins on the way. Could it be that I'm the host of this session here? Because if I leave the session, I have to find a new host. That's what it says.
No, just leave.
Just leave.
He's going to start his. So you leave this one.
Hi, Dave. Hello. Well, I'm sorry. Oh. I think he was selected already. Oh. Oh, hi, Congressman.
Hello.
What I'm not doing is broadcasting to the screen here. So. Oh, I see. Now this. Oh, HDMI. Hold on. Okay. Are you guys seeing my screen? I haven't shared it, I guess.
Not yet.
Okay. That's okay. Nobody can see it. Ah, beautiful. Beautiful. Okay, so I can go here. There's only so much. That can almost reach here. It goes like this. By gum. You should just stand at the board and just like. Oops. I should. Oops. No, I should. Okay, now why am I not seeing it here? Oh, that's bad. I was gonna write by hand on my stylus here. What? This is PowerPoint. Oh. So my point was I was just gonna write on this if I saw PowerPoint.
It should be running through.
I can't write on Zoom.
The screen, if you have Zoom, you can run it. You should be running it from here. You should be running it from here.
Okay, right.
So you should go email, then Zoom, run on Zoom. That's it. This is iPad, right?
This is iPad.
So you get out of that.
Zoom. Yeah, but I can't. This is all gummed up now. I don't even know what this is doing.
You need to just disconnect everything.
Like this, which is.
Okay.
So I don't know. I have this. This is where I leave this. So it's talking to about wireless now.
Oh, you're right. The one.
Yeah.
Oh.
Ah, this is the- Okay. Now, I don't even have Zoom on this time.
We done it. You connected to the thing.
Yes. Wow.
Oh, yeah, I got the actual.
Yeah, it sounds.
You're connected.
Okay.
Just choose the guest. You a guest.
I do not wish to become a wild cat.
I use it on my phone. It's very nice. The whiteboard.
Good.
Doing it, from the drive.
Great, great. So you can show me how to manage this.
It goes okay. It goes down. Now can you get email from here? Do you have your email?
Nope. No, but that's a meeting ID. Right?
Yeah, there's a meeting. Not there. I have it. Here.
922-0857. 7725. Join. Okay, password 290 29049. All right, now I'm zooming.
Now we have to connect this one to it. So there's only one USB-C. You can connect to, unfortunately.
Yeah, so I have this.
That's for your HDMI, but then what do we do with this?
So there's this. Yeah, there's.
Oh, there's a USB. So you have to connect this guy. You can use pointers, but that's okay. To do with it. What's this? Try to, why is it upside down? Okay, join the video.
Recording in progress.
Now we have to connect it to this guy.
Yeah.
One had a little thing on it. I don't know whether this would be this or just.
See you later. Yeah. Now we have much better
seem to have the options that we have.
The other one is just a matter of giving
Yeah, there would be options under sound and
them allows to see this guy.
meeting setting.
And that actually reverses.
I wonder if this guy has an app. Switch camera maybe? Oh, this is the forward backward camera thing. It's a pity.
This is plugged in, right?
Yeah, but I think
Is it on?
well, it's on electricity.
Try to drop out.
No, it's electrical wire. No, I think it's just that it has to choose which, like this one, which microphone to use, which camera to
It
use.
doesn't seem to be an option.
Maybe it's settings. You have to do
She's on her own. So it wants to read it through this. All right.
So let's see.
What if this was seeing this and this was plugged in? Awesome. I can share screens between
Using the meeting. Using the meeting hall. Can I use how the meeting join from my phone or tablet? No, you cannot use how as the camera, speaker, microphone join.
Well, there you are.
This is from the OWL system, OWL Labs or whatever it's called.
Okay, so what are we doing instead?
I think presenting it this way and maybe using the whiteboard. Okay, because this apparently I'm going to read, but it looks like it doesn't allow you to do it.
All right, so we'll
We'll have to switch back.
do this and we'll go. That's unfortunate.
But I love using this for writing.
Yeah.
And Zoom allows you to do that too. So I've used it.
Yeah. Okay, so now this is on
So now you start to Zoom again.
I see.
Email.
Zoom again. That's really a shame. But I hope you have a lot of good whiteboard markers here.
This OWL system does not work with ITAMP. So we cannot somehow allow it to use the microphone OWL or the camera on OWL. But I think we're going to go back to the original thing. So let me see if everything is working.
Look, this is appearing on the screen. That's pretty good.
Yeah, but
This is out of the picture.
yeah, the picture, but I don't see the.
Dave, can you hear me?
Yes, I can.
Oh,
Okay.
thank you. Okay, so now I think, yes. You're set to go. So
Okay.
you started and I
Great.
think this works.
Fantastic.
All right.
So I'll start, okay, all right. So we've decided to move the meeting into next week. To account for the time delays. Hi, everybody, I'm John Bohn. I'm a theorist, holder applause. It's a great pleasure, of course, to be here talking to you, and we have been invited by the ITAMP to come give these lectures. Because of technical difficulties, what I was going to do was to write on my iPad and have my words appear on the screen. This will not happen, so I'll be writing on the board over here anyway. This is probably an advantage of having my handwriting terrible. So. So let's begin with this. So my general topic in these three lectures is going to be diatomic polar molecules in an electric field. I'm going to try to keep it focused on this this single topic here. Go ahead. Can you see this? Here's the go. Is that like everyone? Good. Excellent. Let's go with diatomic molecules. With an emphasis on the following. Emphasis on, first of all, we want polar molecules because we love the idea of polar molecules. Professor Rempe introduced this already. We have the idea that polar molecules have strong, long-range dipolar interaction. And basically, the substance of these lectures is to look under the hood and see what does that really mean? What do you really get? Well, to be polar, you want to look at the electric field effects. Because that's how you manipulate, influence the dipoles of these molecules. There are some surprises along with that. We will think about interactions between polar molecules and strong long-range things. Time permitting, we'll talk a little bit about scattering, which is an important issue of how molecules interact at ultra-cold temperatures. What we will de-emphasize is anything potentially complicated that I'm unable to understand. So we will not think about electron spins. We'll not think about nuclear spins. Because while they are important, they are very difficult and only complicate the issues. You can understand the basic things about the electric field effect without worrying about the spin. Luckily, we have Professor Turnbull here, who's going to tell you all about the spin parts. I can do the heavy lifting, and I am unwilling to do that. So first of all, let's talk about polar molecules. Before we get to the electric field effects, we'll first work our way down. and make a brief survey of molecules in general. Look, these are diatomic molecules. What do you got? There's a positively charged ion, we'll call it A. And here's a positively charged ion over here, we'll call it B. And the space around these ions is surrounded by tiny little dot particles, negatively charged particles that we call electrons. And I put this up because, as I understand it, Professor Rempe doesn't quite know what's going on inside a molecule. So this is for your benefit. Ions and electrons. And the first thing is, there's a swarm of charged particles there, strongly interacting charged particles. And the first thing about molecules, the first miracle is that they're molecules at all. What is this bunch of charged particles? Why isn't it just a plasma? How do they organize into molecules? Amazingly, they do. We do not deserve the molecules to be as orderly as they are. And you know how this works. The first unit is, auto racing. The first unit is this. You say, I'll put the distance between these two. I'll call it R, because I'll leave the letters R for the thing. When I set the distance between the two molecules, I click R, I solve the electronic structure problem. That is, I solve the Schrödinger equation for however many electrons there are out there. This is, as you know, the Bohr-Oppenheimer contribution. And we love the Bohr-Oppenheimer contribution because it works. The big heavy nuclei kind of stand still while the electrons rearrange themselves what they need to do. The molecule is self-organizing in this way. And what you get out of it is, here's a kind of picture that theorists love to draw. Here's the distance between the molecules, and at each distance, each intermolecular separation, there's a whole spectrum of electronic energy states. And as I move the distance between the atoms, the electronic spectrum changes in a continuous way. And what I get is potential energy function R. There's a good example of one. They all look like this, especially when a theorist draws them. They are strongly repulsive when the molecules get close together because they're always electrons in the pair. Satisfy the Pauli exclusion principle. You cannot shove the two ions too close together. There's some minimum, and then there's some differentiation here where in the diatomic molecule case, this represents the energy of the two atoms separated from each other in association. They all look like this, but there's more than one. There could be another one like this, maybe this goes to the same threshold. I don't know. And maybe there's another one that does this, another one that does this, and on and on. How many of these things are there? Lots. There are lots of them because these are electrons. And even if we take one of those electrons and keep looking at its excited state, it sees a positive ion left behind. There's a whole Rydberg series of these things. There are infinitely many potential energy states here. We don't want to deal with that. Some people do, more power to them. What we will know now is that if we think of the characteristic energy scale of these, how deep are these things? Oh, I don't know. Maybe they're 1,000 Kelvin, maybe 10,000 Kelvin, whatever. It depends on the species there. I will use Kelvin as if it's an energy unit because I am a theorist and Boltzmann's constant is equal to 1. 10 to the third to 10 to the fourth Kelvin is not cold. This is not cold. We don't like that. So what we'll do is go to the lowest one. That's the strategy. There's a whole bunch of interesting stuff up here. I don't care. Let's pick the lowest energy service to think about doing it. This is not to say that electronic excitations are not interesting or useful in the optical context. They are. You'll hear examples of that during the week. But where I'm talking about the optical. Once you're in this, you have a potential energy that describes the relative forces between the molecule atoms. Yes.
But also there are different curves.
These are different electronic excitation. So just like that, hydrogen, 1s, 2s, and whatever. These are the analogs of that. But therefore, many electrons, and they're super. And people who are experts at doing these calculations, these people are called chemists. They are good to have this ready. And this is all electronic excitation. We don't care. if we're in the lowest electronic excitation, we have a potential here that governs the way the atoms move relative to each other. And therefore, there can be quantum mechanical motion as well. That is called vibration. There's a discrete set of energy levels here that are called vibration. And their typical energy scales are, I don't know, make up a number like 1 Kelvin, maybe 10 Kelvin, depends how high you go up, 10 to the Kelvin, 10 Kelvin. This is not cold. So the strategy is go to the lowest one. You can see where we're going with this. Ideally, you try to get to the ground state of everything, you know, full limit. You've got the molecules in the lowest vibration, they're not doing much. You think of them as in fact, a rigid rotor. It's not a terrible idea to say from now on, pretend the molecules, the atoms, the molecule are some fixed distance apart. That is approximately this distance. There are details for that, don't worry about it. Now we need to address rotation. So now we have a molecule is something like this, and some fixed interatomic separation that is called RE, give or take. It's close enough for our purposes. And the electrons are some multiplying state around that. And what we're talking about now is rotation. We cannot just go to the ground state of rotation of these things, because we will need to play on the rotation of the rear freedom to understand electric field effects. Okay, this is kind of the background, the scope. This is where our starting point is. And I want to say, what I intend to do in these lectures is to kind of bring up a few interesting topics in ultra-cold rotation dynamics and electric field effects in molecules. I'm going to try to pick a few topics that we tend to throw around in casual conversation when we talk about molecules, but that, you know, maybe it's been a while since you thought about what this actually means, or maybe some of these Dr. Ricky haven't thought about kind of what they mean. So we're going to walk through some of the ideas here. There will be some math, because here's what are you going to do? There will not be much math, because 3 hours of lectures, what can you do? But luckily, there are references for this. I've shown some of my favorite ones here. If you would like to know more about diatomic molecules than you can stomach, there's this spectacular book, Brown and Harrington. It is this thick, 800 pages big, and it is just about rotations in molecules. This is to suggest how much work Professor Sherrill has to do. He gives a lecture to prove the full structure there. It is a fantastic book. It has both theory and experiment. I recommend it highly. Zara's book is probably still the best on angular momentum. Rotation will get you heavily involved in angular momentum. It is a gateway mathematics that gets you into harder stuff like quantum field theory. And then here's a delightful book, Molecules and Electromagnetic Fields, by our friend Roman Krebs, who has written a book that really focuses on the issues that we care about in the ultra cold. So all of the details that I don't know and have forgotten in all the lectures I'm giving today are in this book. I brought it with me, so if I get stuck, we can go see what the master has to say about that. Krebs, Roman Krebs. What? Oh, that's me. I forgot about that. That's not a book, but this is an article that we published in some book. The book is probably hard to come by, but it's on the archive. Many of the things that I will be talking about in these lectures are developed in there as well. Thank you for that. Okay, so now we go over here. We have a rotating object. We have now you understand what this is. These are drawn as little circles. These are basically the nuclei, the molecule. This world massive. Rotation happens by swinging this element. There's no rotation on the local rotation around this axis because these are point particles. So the rotation vector of this, which we'll call R, is hopefully not too confusing, is the rotation, the angular rotation. R for rotation, get it? You get it? And there's a rotational Hamiltonian that goes along with this, which is a number up front, the rotation constant, which is to do with the moment of inertia of the molecule in the ground state here, times the square of the angular momentum. That's how rotation works. And we will put this to use later on. Okay, while we're here, this is just the molecular part, but of course, as the molecule, as the nuclei are doing what they're doing, the electrons go along with the line. And so, we'll account for things like capital L will be our rotation, which is the sum over all electrons I. These are the electrons of the angular momentum of each of the electrons, however many there are. In the end, as you get back to the question, these are all different electronically excited states, but you know, you take them all together, the state of a bunch of electrons. Likewise, there's the total spin, which is the sum over all the electrons of the spin of those electrons. And we find it convenient. This I'm stealing directly from Craig, so I think it's pretty standard. We find an angular momentum n, which is r, the rotation of the molecule, plus the orbital motion of the electrons that go along with it. And then, as if that's not enough, my gosh, take it out here. There will be a final total angular momentum J, which is the sum of n, and then I can throw in the spin. No nuclear spin, so I won't even introduce a notation for that. All right. So far, so good. So these are just vectors. These are ideas, angular momentum. What we want is to construct the molecular wave function that goes along with all these angular momentum. This is interesting, I find. So we'll do this in a little bit of detail. I'm going to claim a lot of things. My first claim is that this is interesting. You tell me that's true. So what we need to do, we construct the molecular wave function with the understanding that the electronic part has been done. We're looking at the rotational part now. And the first thing we need to deal with is frames of reference. This is critical. So here, we're going to have an axis, and I shall call this axis Z, and it points upward in the laboratory. If we're going to apply an electric field to a molecule, the odds are you're applying it along this axis, which is what defines the axis. Along with that comes axis X. Y. And that's fine. We can refer everything to this set of coordinate axes. But you know what? Given that we're dealing with molecules, there's another set of coordinates. Look, here's one of my atoms, and here's another one of my atoms. And that axis determines another axis. Where's the axis? Which I'll call Z prime, which rides along with the molecule. And along with it, there could come an X prime, and somewhere over here, you get the gimmick. This is the laboratory frame. If I want my thumb to follow the molecule, it tumbles around, it will go like this. The carrier coordinates that with it that runs around with the molecule. Coordinates X, Y, and Z, we will call the lab coordinates, and the coordinates X prime, Y prime, Z prime, we will call the body coordinates, because I don't know, the molecule of the body, I guess. I don't know what it is, but there they are. And as well, because the electrons, of course, follow the body frame, they're not really hanging with the molecule. But we don't really do this. This is on earth would you write this down? There's a gimmick. I will now show you. So for now, for us, put it this way, for us, because we are not T-mercial, we will say that the total spin is equal to 0. This will simplify things. That is to say, the angular momentum n, which is rotation plus orbital angular momentum of the electron, is in fact the total angular momentum of the electron. Now we want to transform.
Why are we taking this approximation?
Which approximation? The spin is 0. Because otherwise it's very, very hard. And it's even.
So, is there any physical motivation?
Oh, yeah, the molecules like this, which is, yeah, so. Everybody's real molecules capacity to. Yeah, you can see that, John, clear contradiction. Yes. With the exception of one scientist. Everybody's favorite. And in fact, it's not the best thing to go. It's not linear molecule. And, I mean, it's a molecule. So to transform from the lab frame to the body frame, we do the following. We'll make a wave function. We'll make a basis thing. Okay, well, here's the angular momentum of the electron in the lab frame. It's been zero, yeah. And you know what this is, right? This is saying, I posit that there is a total angular momentum of the electron overlying, which is given by L in the usual way. And essentially, what is angular momentum? Oh, it's this discrete thing. There are a number of states of angular momentum labeled by M and L, which are the projections. These are the eigenstates of the Z component of angular momentum, quantum numbers M and L. And you know there are two L plus one atoms in basic quantum mechanics. So this, this classical continuous thing of angular momentum becomes a nice discrete thing that can handle quantum mechanics. We do that all the time. That's the electron in the lab. The rotation in the lab is given by Y R M R of theta phi. Oh, what's theta phi? By the way, the two frames are related. I should have said that. Here's an angle theta that gets you from the z-axis in the lab frame to the z-axis, and then there's a p-axis also. So if you have a rotating object here, what are the wave functions of objects? What are the wave functions of angular momentum stuff? Oh, they are spherical harmonics. Just like the wave functions of the electron and magnetic spherical harmonics given by the total angular momentum of the projection. Here, the total angular momentum of the rotation is R, and its projection in the laboratory frame is MR. And depends on the coordinates that give the rotation of the molecule with respect to the lab frame. That's a perfectly common wave function.
John?
Yes.
I know that you don't like blue. You may reflect better, or maybe red or something.
Red.
Yes.
Here's the cap for this one. Okay. All right, but it's about to heat up now. Okay, but interestingly, this is the thing I forgot to say, but of course, the relation between these two coordinate ranges is given by, well, the ordinary theta and phi, that would tell you the coordinate axis here. But of course, there's still three coordinates to be given. There's also an angle that runs the molecular axis, which we'll call gamma. And there is a set of Euler angles. Euler angles is the kind of word that's meant to make you shake in fear. You've seen it in other from classical mechanics or something. Is the red one?
I think it works, but in an experiment that's just did.
But the gimmick is, all it really is obviously, I need two angles to tell me where the new axis is, the body axis, and I need a third angle to tell me where I am around that axis. Does it help you better?
Yes.
Yeah, all right. Well, now I can't see it. Doesn't have to be straightforward. This thing, you're right about this, it's also straight on line. Let's not kid ourselves, right? So we have the electron wave function and the rotation wave function in the laboratory. What we deal in is the total angle motivated this before. And so what we can do is the following. Let's say the total angular total angular momentum. And that is to say, in the absence of spin, well, we already decided that's called J, and it will have a projection MJ. And it is given by, in the usual quantum mechanical sense, the sum of MLMR and the LML state here that I have, the YRMR state that I have here, and all this stuff, LML, RMR, vertical line, G and J. This is meant to look familiar, but if it does not look familiar, let me remind you that this thing is a Clench-Gordon coefficient. Another word meant to make you quake in your boots if you're not familiar with it. But what is it saying? You know, just to make sure we're on the same page, let's remind ourselves. Here in the lab frame, we have this angular momentum that has 2L plus 1 different components and L. And this has 2R plus 1 components here. So there's a whole bunch of angular momentum states that stay here. 2L plus 1 times 2R plus 1. Then I decide, no, I don't want to do that at all. I want to talk about things in terms of. And it will turn out that this is just a basis transformation from this set of discrete states into some set of discrete states here, where, as you know, J is not necessarily a fixed state, but J can run the gamut greater than or equal to the difference between the other two angular momentum and less than or equal to the sum of those two angular momentum. And for each of those J's, there are 2J plus 1 possible states of angular momentum there. This is nothing other than a basis transformation within the Hilbert space of angular momentum. Hilbert space is another. I'm going to frighten and confuse here, right? And so a fun exercise if you've never done this, say, oh, you know, we're given L, given R. Count all the states here, and then count all the states here. And do they come out to be the same thing? They should. There's two representations of looking at the angular momentum. There must be a relation between them, and these coefficients are just that linear transformation. That's all that is. It's got all these letters in it because the transformation has all these lines. But that's how it goes. All right. Now we've got the electron orbital angular momentum, the rotational angular momentum. We've successfully combined them into the total angular momentum in a lab frame, which is useless to us. Because we're getting molecules. The electron cares about what it is in the body frame, in the molecule. So now, we will use three amazing facts about the quantum theory of angular momentum. Oh my God. Okay. I'm going to write these down. I'm not going to prove them. Where are they proven? Oh, Zer talks about them. You can learn all you want to know about angular momentum. It's also in here. This friends talks about it also. So look at this. Here's the angular momentum. So fact number one. The orbital angular